and then the floor will be yours. So thank you for coming to today's lecture on nonlinear aspects of clouds and their formation. And we have Professor Vaughan Philips from the Department of Meteorology at Lund University. The reason why I wanted to invite Vaughan here for this presentation is because I've been collaborating in the field of bioacoustics for a very long time, and one thing that bioacoustics does when they're classifying different call signals from humans or from monkeys or from birds is that they classify the sounds into these nonlinear categories. And the basic way that that works is that we have a class of sound that's organized in a certain way, and Vaughan will talk about that. Things like limit cycles, subharmonics, or folded limit cycles, all the way to tori and chaos. And in between each of these different states, you can transition, and those transitions are called, in the scientific world, bifurcations. And this is something I've been doing for over 20 years, working with people in bioacoustics. So particularly for you, Felicita, this could be interesting because people who are doing voice science also classify the phenomena into nonlinear phenomena. And when I met Vaughan, we were talking about this aspect of nonlinearity, and the reason why that came up as a topic was because the first people to deal with nonlinear phenomena in natural phenomena were people dealing with this climate science, or amongst the first people. And so this is really a natural, it's kind of a coming home, at least in our little world here. So I really appreciate you coming, Vaughan, and I'm looking forward to your discussion. So let's give him a big hand.
So thank you for inviting me to talk. Yes, non-linearity is at the core of atmospheric science. So I'm a scientist, but I'm hoping that some of these ideas that I'll talk about today about chaos, non-linearity, will have some inspirational value to your work in music. And I'll show some examples of the attractors and other phenomena that Mike was just talking about. So first of all, I'll say a few words about basic concepts. I'll define what is meant by nonlinearity. Often these terms are used freely without awareness for exactly what the definitions are. So I'll go through some of the definitions of nonlinearity, attractors, chaos, and so forth. And then I'll show instances of nonlinearity in nature, in the atmosphere. I'll talk about atmospheric waves, and I'll give some examples of different types of attractors, and I'll show some results from a recent theory that I published earlier this year about how cloud microphysical systems have chaos and realms of stability, realms of instability. So nonlinearity is defined mathematically. A system has an input and an output. When the input is changed, then the output will change in a way that's not proportional to the input. We say in a nonlinear way. And then we have a nonlinear system. And very, very typically this happens when there are internal feedbacks in the system. Somehow the output affects whatever the quantity is from the input, which affects the output. So feedbacks can be positive or negative.
Could I make a brief comment? So in voice, we have two parts of the system that are nonlinear, non-proportional systems. So from the power, which is the air, which is funneled into the vocal folds to produce the sound, right? That's a hugely nonlinear function. And then at the top end of the vocal folds, when they produce those little ugly squawks into the resonator, is the second part that is also nonlinear. And then at the end, of course, there's the feedback system loop from the lips back into the resonator. So
fascinating.
That's something that relates directly to what.
And I think dynamical systems generally in nature, whether they're biological or non-biological, they will have some feedbacks. So everything is interconnected with inside a system that has any complexity. So in mathematics, we can define an equation as being nonlinear if it cannot be written as a linear combination of its own input variables. And typically what this means is that the equation must have some higher power of the input. So this is a nonlinear equation because we have x to the power of something bigger than 1. But this is nonlinear, this is linear. So this is a nonlinear equation, but this, I think, would be linear. So dynamical systems in nature are usually nonlinear, and there are various properties of nonlinear systems. Chaos is one possible property. So chaos means that there's a sensitivity to initial conditions as the system evolves through time, such that the system becomes unpredictable at long times. So the atmosphere is one example of a chaotic system, and the chaotic nature of the atmosphere is the reason why it's impossible to predict the weather more than 1 or 2 weeks in advance, something like that. Another feature of chaotic systems is that there's a non-periodicity. So here I have an example of a chaotic system.
Oh, because you're now on the Mac. We had a transfer from the PCs to the Mac, and so it's not reading the file. Do you know which player you were using on the PC? It's probably MP4 or something like this, huh?
I can't remember. Anyway, whatever.
You know
maybe
what you could do?
I could.
You could just play from your computer, just on the
Yeah,
top here, without projecting it.
Mm-hmm.
No, without projecting. You can just turn it around and show us on from your laptop. No,
Yeah.
without that, yeah. Might even get on the camera.
So here is an example of a chaotic system. So this is a pendulum which has got a joint. It's actually two pendulums, one attached to the other, and you see that it's very messy and unpredictable, and the frequency varies all the time.
Yeah.
So here it goes again.
Yeah.
Anyway.
So in the theory of nonlinear phenomena, they often talk about chaos being unpredictable within a defined space,
Yes.
a controlled space or whatever.
Mm.
Do you want to? Is that important to you or not really?
Yeah. So often a system will be stable, unstable, chaotic or non-chaotic in different parts of its base space.
But that thing about being within a defined space, I guess the importance of that is just because it's what you're looking at, right? It's the phenomenon you're looking at, and it's within a certain area. Otherwise, then you'd be looking at something else. I guess. Is that the idea?
Sort of. I mean, there's differing degrees of sensitivity to initial conditions in different parts of the phase space, but the attractor will be where there's more predictability in the location. But an attractor can have a fractal quality as well. So it can
I mean, everything will be basically predictable except for chaos. Right? A torus is completely predictable.
Yeah, there's order in the chaos. You know that the system will be attracted to some part of some set of points in the system.
So are you using as an equivalent the words chaos and nonlinear? No, huh?
Almost, but
because the way that I've learned about nonlinear systems is that chaos is the fifth attractor state, and that before that there are other attractor states that often lead to chaos. But for you in climate science, then chaos is nearly the same thing as nonlinearity, or?
Yeah, chaos means sensitivity to initial conditions and unpredictability. Nonlinear systems are unpredictable. They're unpredictable because of that nonlinearity. So,
and the way that we learned about it in bioacoustics is that the unpredictability are those bifurcations between the 5 or 6 different attractor states that are listed in the literature. Does that make sense? So it's the bifurcations that are the unpredictability until you get to chaos, which is by its nature unpredictable.
Yeah. Sort of. Bifurcations are a manifestation of unpredictability. They increase unpredictability.
The way that we learned about bifurcations is that they're unpredictable because one or more of the parameters have been weighted in a certain way that have them jump to the other attractor state. So, it's like...
Yeah. There are differing degrees of chaos, differing degrees of unpredictability. In fact, you can measure the degree of unpredictability or chaos from mathematically by what's called the Lyapunov exponent, which is so even a system that has no bifurcations and if it only has one attractor, it can be sensitive to the initial conditions. So, for example, if you have two parcels of air that start off at slightly different locations, as time progresses, they will go on differing, increasingly different trajectories, but they don't actually have to suddenly jump to some new meteorological state.
Yeah.
So it can happen gradually as well.
Yeah, I think probably I'm getting in the way of your presentation because Lorenz, who was one of the early people to deal with nonlinear dynamical systems, was a weather person, right?
Yeah.
And so he talked about different attractor states, but perhaps that isn't really kind of part of how you're dealing with the research in climate science nowadays, because it's quite an old idea, you know.
Yeah.
The different attractor states.
Well, we do.
So when you
we do communicate with Lorenz's theory.
Yeah.
Well, when I was a postdoc, Lorenz himself came to the lab where I was working at Princeton, and he gave a talk, and everybody attended.
Wow.
And he had been doing quite a lot of innovative work until that late stage.
Wow.
I mean, I think ideas from chaos theory should come more into meteorology. And so, but people have been making advances by taking ideas from statistical physics or from chaos theory and bringing them into meteorology. And Lyapunov exponents are something I'm trying. That's my next thing on the agenda for my research. So,
do you want to explain what that is for him, or you can do it better than I can?
I'll get on to.
Okay. Sorry.
I'll get on to. So nonlinear systems have these properties. Often they're nonlinear because they involve feedbacks physically, and the feedbacks allow oscillations to happen. So self oscillations can be non-periodic, as we saw with the double pendulum. Another feature of nonlinear systems, like the atmosphere, is that there are interactions between many spatial scales. So energy goes from one spatial scale to a completely different spatial scale. So, for example, surface waves on the ocean can transfer the energy to much bigger waves. So there can be very big freak waves now and again. And so non-linear wave dynamics explain this kind of thing. So there's some mysterious things about waves that still are not fully understood. There can be multiple equilibria, and you see that with the Lorenz. This is the Lorenz attractor.
Right, that's called a torus.
Possibly.
Yeah.
There's an attractor and there's an attractor. So you have two equilibria. So the attractor is a stable equilibrium. So if you start the system right at the attractor, it just stays there.
Yeah.
So
could I just mention one thing about the picture? So the idea behind this is that you have two independent frequency contours within the same system. So that's the whole idea between the left and right. Okay, sorry.
Interesting.
So it's a
there's a different intrinsic resonant frequency, different time for orbiting each.
They should be independent in some way. Yeah.
Right, interesting.
Amplitude, frequency, whatever.
And yeah, limit cycles are another example of property. So so a system can go in a loop indefinitely.
So why would we have flutter of an airfoil? An
Um,
airfoil
well-
like on an airplane, or?
Yeah, if you or if you put anything in a constant airflow, it'll flutter. If you put a flag, or if you put
Yeah.
a rigid thing that can move, and it will. If you have constant wind, then the flutter will have a constant cycle. So it's an example of a limit cycle.
So limit cycle is nearly periodic motion. But what's an airfoil then? That's a part of an airplane, that's the wing, no? Or what's the airfoil?
Yeah, it could be an aerofoil. Like if one flies by, I don't know, Ryanair on the yeah. Okay, that's another story.
But I guess I don't know what airfoil means in this case. What airfoil refers to?
I think so. It's anything that's aerodynamic. You know, a wing is an aerofoil.
Yeah.
It's shaped with a curve
Yeah.
for lift.
Yeah.
It's an aerofoil. I think it should be AERO. So in the atmosphere, something striking is turbulence. So fluids have the possibility of becoming turbulent. Turbulence is defined as chaotic changes with time of the dynamical state, pressure and velocity. And when there is turbulence, even though there may be some damping of motions, the kinetic energy is enough to overcome that. And kinetic energy in one part of the fluids causes kinetic energy elsewhere. And turbulence consists of eddies on all spatial scales down to some minimum size.
Could I? So viscosity refers to kind of like a damping effect on something, and so that's why kinetic energy. That's why it's an important phrase, because you have this inherent damping on the system, but in some cases, in many cases, right, the kinetic energy overcomes that damping.
So if the kinetic energy is below a certain threshold, then it all disappears. But above a certain threshold, the kinetic energy can migrate through or be transferred throughout the fluid in terms of the motions of these vortices. And with turbulence, there's this transfer of energy between spatial scales. So vortices that are big will trigger vortices that are small, or they may trigger vortices that are even bigger. And so fluids have this curious bifurcation possibility, to use your word. So when the laminar flow gets to a certain threshold, then chaos begins.
Laminar means smooth.
Yes. So you see both states of the fluid here.
Yeah.
So this is a candle, and the flow is laminar. I think the flow is accelerating during ascent because of the buoyancy of the air from the candle. This is all air, this is a candle. And when the kinetic energy reaches a critical threshold, you have turbulence. And very suddenly the flow goes from being laminar to being turbulent.
Yeah.
And we...
And that's because of the damping? Because of the viscosity?
Yes, yes.
Is it also that it loses power as you go further away from the flame? Or no? Or the viscosity rises in proportion to the kinetic energy from the flame?
No, the viscosity is more or less constant.
Oh, okay.
But what's changing is the kinetic energy. So the flame is hot.
Yeah.
It makes the air buoyant.
Yeah. Yeah.
But the buoyancy is a force.
Yeah.
So it takes time for the air to be accelerated. So the air's rising slowly here, even though it's hot, but then it speeds up and speeds up and speeds up. And if you look carefully, maybe you can see that the flow narrows a little bit. So what's happening is there's an acceleration, and when the kinetic energy gets to a critical level, there's chaos.
So it has to do with speed, it has to do with the narrowing, like the funneling of something?
Yeah.
Does it, and viscosity also, or not really?
Yeah, viscosity. So you can predict exactly where the chaos will start, the turbulence will start here, if you consider the Reynolds number.
Oh, yeah, yeah.
So the Reynolds number is the velocity times the width of the jet, or if there's an obstacle, the width of the obstacle, divided by the viscosity.
Okay.
So all the way up here, v, the velocity is increasing. So the Reynolds number is increasing until it gets to the threshold at which turbulence happens. And for the atmosphere, we know the critical Reynolds number for the onset of chaos. So it's something like 1,000. So if you calculate this, if you estimate what the Reynolds number is in the atmosphere outside, V perhaps is 10 meters per second, maybe 1 or 2 kilometers up in the atmosphere. L is huge, maybe L is the width of the flow of the atmosphere. So up there, L would be perhaps something like the depth, half the depth of the troposphere, maybe. Let's say 5,000 meters. 10 meters per second, 5,000 meters, divide by mu. And I can't remember what mu is, something quite small, but this number comes up to be about 10 to the power 7, 10 million. And the critical Reynolds number is maybe 1,000. So the atmosphere is always turbulent, in the turbulent regime. So there are eddies all the time in the atmosphere that are turbulent.
Even when there's no wind, no human-powered devices, a very calm area will still have a lot of turbulence in it.
The energy of the turbulence has to come from somewhere. So if there's no energy, then well, I guess. So yeah, if there's just a still day, then V will be very small. So the Reynolds number will be small if conditions are very still. So turbulence distinguishes some clouds. So we have 3 cloud types in the atmosphere, most broadly. So we have convective clouds that are powered by the buoyancy force. So when air is warm, it rises because it's positively buoyant. Convective clouds are turbulent, they're relatively narrow, they have fast vertical motions. We also have layer clouds, stratiform clouds, which is caused by just large-scale ascent in the atmosphere. We have cirriform clouds, that's the same except it has ice in it. And here's a photo of a convective cloud. So because convective clouds are narrow, relatively, you can see them in their entirety, if you're lucky. So this is a thunderstorm viewed from a distance. So you know it's a thunderstorm because the top is very high and very flat, and you can see it's very dark below because of the rain, intense rain. So convective clouds have vertical velocities bigger than 1 meter per second, intense rainfall, intense radar reflectivity, large precipitation particles, so hail, for example. And the deepest convective clouds are as deep as the troposphere. So this is the top of the troposphere. So stratiform clouds are the opposite. And so one example is when there's a snowfall in winter, so snow will fall from nimbostratus cloud, usually. So now I'll say a few words about waves in the atmosphere. So this is quite sort of relevant to music. But waves are fundamental in meteorology as well. So a wave is an oscillation that propagates through space and time due to the oscillations of individual elements making up the medium. So each element is not propagating, but its movement excites movement in adjacent elements and so forth. And there are 3 basic properties of a wave. There's the amplitude, the wavelength, and the frequency. And something striking about waves in nature is that they have a characteristic time period or characteristic frequency. It doesn't really matter what the amplitude is. So in meteorology generally we have about 5 types of wave in the atmosphere. Sound, I'm sorry to say this, but for meteorologists, sound waves are a pain because they wreck our weather forecasts. And I think the very earliest weather forecast failed because there were actually sound waves in the simulation that made noise build up and the forecast crashed. But very soon people worked out a way of filtering sound waves. So I'm sorry. But people wanted good weather forecasts. So there are gravity waves that are fundamental to clouds, and gravity waves are also important for the climate. But the most important waves for the weather conditions are baroclinic waves or Rossby waves. So these 2 waves are quite closely connected. So the gravity wave is created by what's called the buoyancy force. the Rossby waves are created by the Coriolis force. The Coriolis force acts effectively horizontally.
Can you give us a deeper, so it's horizontal, and what about it?
Well,
What's special about the Rossby?
so a Rossby wave propagates fairly fast because it's a very large wave. So Rossby waves are many thousands of kilometers wide or long in terms of their wavelength. Because the Coriolis force is a fairly weak force, the Coriolis force is important on big spatial scales and big time scales. So it's a relatively weak force compared to forces we're familiar with, but it becomes appreciable over long time scales. So a parcel of air moving around the globe, following the mean flow from west to east, it will experience a Coriolis force to the right of the motion, I think, in the northern hemisphere, and usually there's a pressure gradient force balancing it, so it goes in the opposite direction. And so if there's an imbalance between the Coriolis force and the pressure gradient force, there'll be a sort of circular motion. So the Coriolis force varies with latitude. So if you take the parcel and move it to a different latitude slightly, there'll be an imbalance between the Coriolis force and the pressure gradient force, which will tend to cause an oscillation. So parcels will oscillate around the latitude, their initial latitude. So the Coriolis force acts to the right of the motion in the northern hemisphere, and so the Coriolis force always tends to create circular motions. So the Rossby wave sort of consists of sort of circular-like oscillations. And baroclinic waves are caused by horizontal temperature gradients that create a sort of density contrast horizontally. And so baroclinic waves will involve ascent, and due to the buoyancy force from that contrast, and there's vortex stretching.
Is it similar to amplitude and sound, or not really? If you have an increase of mass or whatever, because that's
I don't know. The sound involves just the pressure force. So these waves are I think transverse. I think so. Sound involves the pressure force acting in the direction of propagation. But I think with these waves, the force is acting perpendicularly. So these waves are more complex.
okay. And does something cause these waves, or?
Yeah, so there's energy arriving all the time in the climate system from the sun, and then that's converted to long wave energy. There's thermal heating, and there's evaporation of water. So water condenses in storms, and then there's latent heat from condensation, and and so one wave continually causes another wave, so there's a continual sort of cascade of energy among Rossby waves.
So if we didn't have a planet that moved, if we didn't have a planet that rotated, then we wouldn't have those waves?
Not in the form we know them.
Yeah.
No.
But will we have them at all?
Well,
because I'm trying to think. I'm locked into this idea of a wave being caused by something, and maybe that's the wrong concept.
But I think, a wave has to get its energy from something.
Yeah, right.
So,
that's
or turbulence. Or there has to be some stirring of a fluid in order for there to be turbulence. So these waves get their energy from the sun, ultimately. The sun causes evaporation of water, causes long wave heating, and so many systems of clouds cause horizontal motions that then excite these waves.
What about the furthest out planets in our solar system? What about the ones out past Pluto? Do they rotate? Do you know? Does Jupiter, Venus, do they rotate?
I think they all do.
Yeah, okay.
I mean,
I guess so.
Even the satellites.
I think there are these waves, and you can see manifestations of them on the surface of Jupiter.
Okay.
There's
Who's Rossby? Who's Rossby?
Well, he was. I think he was a Scandinavian meteorologist from the beginning of the last century, around the 1900s, something like that.
So he was the guy to document this.
Yeah, he discovered Rossby waves. Well, the Scandinavians sort of did a lot of progress in meteorology. So there was a whole school of people like him in Scandinavia: Rossby, Findyson, Berggren, around about 100 years ago, and they started the first sort of network of observing stations that was then used to predict the weather. So meteorology sort of restarted in Scandinavia. So if you fly on an aircraft, this is quite a familiar sight. So you should always get a window seat when you fly on an aircraft, and then you can look down, and you see patterns in the cloud in the boundary layer. So in the lowest kilometre above the ground, we have what's called the boundary layer, where moisture is trapped, where there's a lot of turbulence, and typically there's cloud at the top of the boundary layer. It's just a very thin amount of cloud, and as the air moves over the land, there will be obstacles that trigger gravity waves. And you see that the waves show up in patterns of the cloud.
So in this picture, which way is the wind moving? Is it moving left to right or right to left? Or they're different?
It's difficult to say.
Because it can go like this, right? It can cross.
Well,
all sorts of different streams.
It's impossible to say really.
Would it be going like this? One going like this, and then another one going like this, or no?
Yeah. I mean, there can be waves going in all sorts of directions. so let me unpack the different ideas here. So cloud formation relies on ascent. So any cloud is just condensate that's appeared, and usually the condensate only appears if there's some ascent, because as air rises it cools, and the cooling creates the saturation that creates the condensation. So when you look at these lines of the clouds, what you're looking at is lines of ascent. So all these parallel lines of clouds are in fact parallel lines of ascent. So here's a cartoon. So here's an obstacle. The air is going this way, and if I'm a parcel of air, I just go with the flow.
Well, you do play violins.
So, yeah. String players always go with the flow.
So that's the string theory.
And so, but if I am a parcel of air, I have a sort of characteristic frequency of oscillation. So I will go up and down with a certain time period. So if the kick that is given to me sort of roughly coincides with my natural time period of going up and down, then there'll be some resonance, and I'll keep on going up and down at that same frequency. And so if I go up and down like this, because fluids are continuous, I will excite all my colleagues to go up and down in a similar way. But what's interesting, when you look at this, you see that although the flow is going this way, there's a sort of a slope of the peaks of the waves. So energy somehow is going upstream a little bit. And you see that there can be eddies near the ground excited by these waves. So gravity waves can have wave breaking. There can be turbulence.
Could I ask a simple question?
Yeah.
So if the wave is moving from left to right on the picture here,
Yeah.
the resonance system, the air particles are kind of like, it's densely or more loosely packed, and so they're basically going like this, right, and bumping into the next one, and then bumping into the next one. The resonance of this area, while the air flows through it. Is that correct?
Yeah. So
Okay. And then
Well,
how high up
well,
can you talk about resonance? Like, could it be?
it could be many kilometers up, and so there's a crucial detail here, which is that the so what's causing me to oscillate up and down is my buoyancy. So I become more buoyant than surrounding air when I'm lower than usual, and that accelerates me upwards. But when I'm higher than usual, I become less buoyant than the surroundings, and so even though I'm going up, I'm negatively buoyant, and eventually I just go back down again. So there's this interplay between my temperature and my speed. And you can quantify whether there's going to be this resonance. So N is something that characterizes the vertical temperature gradient in the environment. So, so let's say Z is the altitude of a parcel, and this is the buoyancy force per unit mass of the parcel. The buoyancy force is the upthrust from the surroundings minus the weight of the parcel. So when a parcel is at rest, it's neutrally buoyant. The buoyancy force is 0. So the vertical acceleration is just the buoyancy force. And by Archimedes' principle, you can write the buoyancy force as this. And then by the ideal gas law, you can write it as this. So if a parcel is anomalously buoyant, so then it will be anomalously warm compared to these surroundings. So this is the surrounding temperature. This is the parcel's temperature. So if a parcel is warmer than the surroundings, the fractional temperature difference times g is just the acceleration.